Now, so it's a great pleasure to welcome Michael Breakspear as our keynote speaker. Michael is the Professor of Neurosciences at the University of Newcastle and Group Leader of the Systems Neurosciences Group. His interests lie in the basic principle of large-scale brain dynamics, how they underpin perception, inference, and motor control. And as a psychiatrist, his work contributes to the major mental health illnesses such as schizophrenia, autism, and dementia. So welcome, Michael. We look forward to your talk, Using Physics to Understand Brain Disorders.
Okay, thank you very much, Matthew, and thank you to the organisers for inviting me to come and present some of our work. It's a huge swivel from what we've just heard about a national response to the pandemic or statewide response back to some very basic neuroscience. I've also, in keeping with the workshop or the symposium goal, taken a big picture on some of the work that my group and I have done over the last few years. And so there is quite a lot of material, and I have to apologise. I will gloss over some of the details and hopefully give you the big picture. As Matthew said, I'm at the University of Newcastle, and as such, I'm on the country of the Awabakal people, and like to acknowledge their country and their connection to country. This is my newly formed group at Newcastle, but the work I am presenting, Using Physics to Understand the Brain, actually derives from when I was a student and a postdoc at the University of Sydney. There's four components to my talk. The physics of stuff, as I've nondescriptly described my introduction, and showing how that then translates to understanding preterm neonatal cortex and some of the challenges it faces. Then another rather nondescript, the vibes of the things. This will all be disclosed in due course, and showing how that can also be used to unpack some of the sleep stage phenomena in neonatal cortex. So from some very basic principles of physics in the brain, rapidly translating to what we've done around clinical neuroscience. Okay, so as a clinical prelude, this is a long story that I started with my team about 6 years ago with Samson van Hartelo, who was visiting Australia on a Marie Curie fellowship and presented with EEG data from the extremely preterm neonate. And this is a very perilous time for the newborn brain. Up to 50% of these extremely newborn preterm neonates can have intraventricular hemorrhage. And this often leads to long-term disability, which is typically measured from 2 years of age. Samsa said to us at that stage, we really lack good predictive bedside tests in this time window. And he was a big fan of clinical EEG, which is why in Finland Dad acquired all this data that I'll come to. In a nutshell, the moment of extremely preterm birth, the EEG looks like what I show on the left, a flat line, which is basically nothing but amplifier noise. Within a few hours to a day or so, it has to transition to this continuous EEG over on the right-hand side, which looks to some degree like adult EEG. And it goes through this characteristic pattern of burst suppression, where the flat trace is interrupted by these high amplitude erratic bursts. So the neonate really has to go from the left to the right as quickly as possible. So just stepping back from the clinic, if we just think of the brain in a very, very extraordinarily simplified framework, here's the setting of acute depletion of metabolic resources at the time of birth. This also happens following hypoxic birth, which I'll come to as well. You can think of the neurons as being utterly depleted of their metabolic and perisynaptic resources to fire action potentials and excite each other. Then after minutes to hours, intracellular processes replenish some of these metabolic resources, and we get this burst suppression. So rather than going into deep physiological detail, I'm going to truck in completely the opposite direction and consider the brain in the most fundamental way possible, putting the hat of a physicist on. And this is just a system of interacting units. Then we're going to put some heat, glucose, entropy, it doesn't matter. We're just going to heat this system up and then have one electrode that records what's going on. So it could be sound, it could be electrical activity. This incredibly simple model can tell us a lot about how energy drives the units of a physical system to interact, as I'll show shortly. A canonical system that physicists have studied for hundreds of years is this one, or at least for over 100 years, a ferromagnetic sample with a coil, which creates a field. So now we've just got this very simple system, this metallic object, and we're increasing an external electrical field. If we zoom in on the magnet, we see it's composed of these spins or dipoles. And the spins can be described. I'm not going into many equations. This is just a simple linear algebra. We've got this external field H, then we've got the influence of local neighbours on each other. These dipoles like to line up next to each other. And then because it's a real system, we've got some impurities. So just three terms only need to be thought of metabolically. And that is this external field that we're applying, and the interactions amongst the spins like to make everything uniform. And so that's the ordering force. And the heat, the kinetic energy, and the impurities in this system create disorder. So this is like the archetypal battle between order and disorder in a very, very simple system, which actually turns out to be remarkably complicated or complex. So I'm going to play some sound. It only goes for a few seconds, but we start off with absolutely no interactions in this abstract system and modeled with that simple equation. So it just behaves exactly like the thermal energy that you put into the system. There's no interactions, there's no order, there's just this noisy time series. And if we look at the mean of the energy, it's got this massive peak, which is the mean energy, root mean square of the energy that we put in. I'm going to represent that distribution in a log coordinates. That's why it looks like this. This is commonly seen, for example, if you turn the television on and you don't tune it in, you'll see this sort of hissing white noise. Now, what happens if the interactions are weak? So some of the particles start interacting and colliding and forming these small local domains, and that's called popping noise. This causes the amplitude of these fluctuations to go up a little bit, but on this log linear coordinate, it still drops off fairly quickly. And there's one simple exponent that gives this a characteristic scale. So this still more or less has the scale of the energy that you put into it. And another common way of experiencing a process like this is just to put milk into a bowl of rice bubbles, and each rice bubble has a characteristic size, and when it interacts with the milk you hear the little pop, And that really is exactly what's going on in a system with just weak interactions. So they can't build up beyond the size of the rice bubble. So obviously the next one gets more interesting. That's when we have moderate interactions and moderate disorder. So this just gives rise to something that physicists call crackling noise. Crackling noise, because these interactions build up, we get louder and louder noises, but they occur very erratically. You might have recognized the sound of a fire or something. That's because this is very much like a fire. And when we plot this, we see this straight line now in log-log coordinates. This is a system which has no scale. So all scales at some time of your recording are expressed from the very small scale fluctuations up to these large events that incorporate nearly every part of the system. I'll come back to this in a moment, but there's many examples of these scale-free systems in nature. These are the beautiful videos that you may have seen, starling murmurations. And this is a classic example where the birds are flying in these clouds and they're really just responding to the birds in their very vicinity. But because they do that quite strongly, you get these large patterns that involve the whole flock. And physicists have studied this and shown that this is quite formally a scale-free system. Then we can make the interactions stronger until they overwhelm the disorder. And we get these huge events or domains. And this is called snapping noise. In Sydney and up here in Newcastle, just 2 nights ago, we had a great example of this in a beautiful thunderstorm. So all the energy builds up and then explodes or is discharged in a very large event. And that's an example of snapping noise. So these all came out of this very simple model with just heat, an external force, and some impurities. And the interesting one, as I said before, is this crackling noise, where these two opposing forces interact and cancel each other. So we've got events at all scales. And I mentioned before that this is a very common type of phenomenon. Fires, murmurations, the financial stock markets when there's high volatility, these all show these scale-free fluctuations. And the really interesting thing is, for a physicist, that the actual details of the system don't really matter. All that matters are that their units, could be neurons, could be atoms, that interact and like to synchronize, but also need to overcome some disorder. Of course, no system is infinite in size, and so it's important that when you put these systems in a finite bucket, you get this truncation of the right-hand tail. So I said to Samsa, let's have a look at your EEG. There's the flat one, there's the burst suppression. Let's have a look at these bursts to see if they're actually scale-free, and what happens when the babies recover, what happens to these burst statistics. So here's an example in a little bit more detail. We just square the EEG to get power fluctuations. And if you magnify them progressively, you sort of see bursts that look small can be magnified and become big, and then there's bursts near them that look small and you can magnify them and they become big. If you play it just through an amplifier, it actually has this characteristic sound of crackling noise. So there's now quite important standards for analysing these sorts of data. You need to use model comparison, model likelihood, My postdoc and student, Cortical and James Roberts, did all of this. And we were able to formally show that these neonatal bursts satisfied these criteria of scale-free statistical properties. And these go off across, I might say, a remarkable 6 orders of magnitude. So some of these bursts, you could think of them as having the scale of a millimetre, and then the very large ones would have the scale of a kilometre. That's the order of magnitude difference. And their area and their bursts duration both are scale free, and they scale as well. The area versus the burst also scales, and you see those insets. And when you look at the relationship between them, physicists have shown that there should be a universal relationship between them, and that new plot shows that this is the case. You know, these babies are basically evidence the hallmark of a very, very basic physical system. Now, because there's noise in the system, you can model it as a random noise. So at any time point, there's an equal likelihood of going up or down. That's what that x dot equals at psi show. If psi is noise. So the system changes, that's x dot, completely noisily. This is a random walk, probably one of the simplest equations you could write down. It's just linear on both sides. What's interesting is, although these fluctuations look very unique and irregular, if you bin them in durations and average them, you get a perfect semicircle. And it doesn't matter what the duration is, if you bin them together, all the fluctuations converge to this universal shape. Something else very interesting that physicists have come up with. So this random walk yields scale-free shapes and the power law scaling. So what about our neonatal EEG? What do these fluctuations look like if we submit them to the same process? So we do this by expanding them or magnifying them, picking out the bursts, and then averaging them together. And as the physicists do, we take these averages in very short, slightly longer, medium, and very long bursts and ask simply, do they show this fingerprint of universality? This is what they show. On the top left is one baby, and on the below that are the shapes of all babies. So the answer is, well, they nearly show this universal shape. But what happens is that at longer time, when we average the longer fluctuations, they begin to lean to the left, and they actually get a little bit flat. So they get flat, they get tented, that's kurtotic, and they lean to the left, or they get skewed. That doesn't happen in the simple equation, which is completely scale-free. If we put a little term here called minus lambda x, that means when the fluctuations begin to get a long way from the origin, there's a forcing term that pushes us back to the origin. We get flattening, and with some insight and maths, we discovered, this is a little bit complicated, I know, for neuroscience symposium, but if we made the parameter lambda collect the recent history of energy from the system, and I'll try and explain this in a moment, then we get these fluctuations leaning to the left. And actually we get a very close match to what we had observed in the data. In the babies, the left would skew more or less goes away once they recover. So what is this term that I've put on the screen? So x dot is the noise with the damping, and the damping is got this integral It just means this important term I've put the box around, x squared, is the energy. So as the energy of the system is expressed, it gets more damped and the burst comes back to zero. This suggests that in the neonates, as the activity comes back, it's like a car with hardly any petrol. And you drive up the street, but you use the petrol and you conk out, and then you have to wait for the petrol tank to fill back up. This is obviously not how our brains work. If we exert mental activity, we certainly don't expect to fall asleep or drop into a coma after a few minutes. But in the neonates, this really speaks to just how close they are to being metabolically depleted. So we have these little metrics now. We have a baby, we have its power law, and we have the bursts. And we can now ask, do they relate to clinical outcomes in the babies? The first thing we just did is to group the babies by gestational age. This is the number of weeks, should be 40, but these babies are born between 22 and 28 weeks. And we see quite clearly, just by color coding them, that the birth shape is far more skewed in the very early stages or the very early preterm babies than in the later preterm babies. And we've followed this up to show that there's a strong association with birth shape and gestational age. It's like a neonatal growth chart of electrical activity. These change because Samsa had EEG acquired for 3 days following preterm birth. These statistics change quite quickly following birth, from 12 to 72 hours. This is the skewness, the kurtosis, and the slope of the scaling relationship. And moreover, I'm just briefly showing here that they also change in a way that predicts or preempts outcome at 2 years, as measured by the Mental Developmental Index, or the MDI. And you can actually use these measures with a receiver operating curve to get quite good accuracy, sensitivity and specificity in a very brief EEG recording, and it can all be done automatically. We had some other EEG data from hypoxic neonates. So these were born at birth, but following a complicated delivery or an end of pregnancy illness. And many of these hypoxic babies, they also show birth suppression. And some of them at 3 or 4 days show evidence of intraventricular hemorrhage on ultrasound. But you can see at 6 to 12 hours, we can already detect the likely underlying presence of intraventricular hemorrhage according to the birth shape. And once again, no time for details, but these metrics predict very sensitively the presence or absence of underlying intraventricular hemorrhage, likely because the babies who have hemorrhage are the ones who have the most, the deepest metabolic insult and the less metabolic resource. And therefore, if you think of that equation I showed, the most effect of any burst depleting what had recently recovered. Yeah, and we actually, this is my one and only ever patent, and we patented it and we've replicated it. Now, that ends that part of the talk, and I know I've gone quickly. I've only got 5 minutes left, so hardly any details here, but this is something we did last year which I think is really, really interesting. And I'll just very briefly show some of the insights. What about the spatial dynamics? So we just had one recording, but the brain is spatially extended, and we had lots of electrical recordings. And so could we use physics to understand the whole brain activity and not just one summary recording? So to do this, once again, we went back to physics. This is a plate which is vibrated at increasing energy and which shows these beautiful patterns if you just put sand on it. The sand settles on the part of the plate that's not vibrating. And as you increase the vibration frequency, you see these beautiful patterns appear and then reorganize. Vibrations on a plate obey what's called a wave equation. Don't worry about the details, but you can solve this and you get something called eigenmodes. These are the fundamental frequencies that this plate supports. It's like a guitar string, but it's in 2 dimensions, or a piano string, or whistling into a bottle with some water into it. So these natural systems like to vibrate, and they vibrate in a way that depends upon their geometry, basically. Now, I worked as a postdoc in the School of Physics at the University of Sydney with Peter Robinson. Peter and others worked for some years on a wave equation for the brain, following very similar principles as for a plate, believe it or not, but also with a lot of embedded physiological detail. And I did a postdoc showing that you could use this equation to predict and understand epileptic seizures and alpha activity. But you can also do something called the Laplace of decomposition on the wave. And in essence, you can find the fundamental harmonics of the brain. These are the low order modes. And then you can express brain activity as being a sum of these modes, each of which have some temporal frequency. So the low order modes, the big modes, carry very slow frequencies, and the high order modes, the more complex one, have higher frequencies. So yada, yada, yada. I have no time to explain this, but we went back to the babies. We looked at all the EEG. We had active sleep, we had quiet sleep. We did something in network science and we got these great patterns. These are the differences in electrical activity in newborn preterm neonates from active to quiet sleep. So much more connectivity in quiet sleep and a little bit more connectivity in active sleep. And some differences between the groups, and some differences between the preterm and full-term infants between active and quiet sleep. This is an interaction. In essence, when full-term neonates fall asleep, there's a big change in their brain activity. When preterm infants fall asleep, even when the brain activity is recorded at full-term equivalent, the transitions are much smaller and highly significantly so, and also associate with outcome at 2 years. So this was all fine and dandy, but then James Roberts said, let's try and model this with these brain modes. And in particular, we'll just pick 3 of them because it looks like they're the modes that change when the babies fall asleep. So we did this. We have data on the left, we have the model on the right. These are the carrier frequencies. We used a pretty simple fitting algorithm, and then we could get the baby and the model to look like each other. We could fit all the babies to the model, and it works really, really well. And then we could now look at how much energy was in the modes between the different sleeps. And not surprisingly, there are changes in the brain modes that also differ by group and sleep effect. I'm not going to go into the details other than to say the model performs just as well as this network analysis of the data, but it gives a greater insight. Okay, I'm out of time, so I'll summarise. We can develop clinically relevant bedside measures from low-cost technologies using simple models of the brain. Australia needs more investment in keeping bright young people in science rather than expensive new imaging equipment, of which we now have plenty. We only do these collaborations by physicists, neurophysiologists, neonatologists working together. And I can tell you a lot of bright young people in these fields get disillusioned with the funding outcomes and get work in industry. And I think the work is very interesting and has loads of translational potential. Just finish by acknowledging SAMHSA in the middle and the postdocs and students, and Peter Robinson, who was my postdoc supervisor at the University of Sydney. So thank you.
Well, thanks, Michael, for really fascinating insights into the snapping, cracking, and popping of the brain function. So, look, as before, we've got time for questions. You can put them through the chat room. Just to start it off, I suppose, Michael, you talk about the burst suppression patterns, and they can be obviously evidence of brain dysfunction, but I suppose also the therapies that these neonates might be getting in the ICU environment. So can you distinguish the burst suppression pattern from physiology versus drug effects?
Well, Matthew, it's a difficult question. I mean, SAMHSA's team had gone through hundreds of babies to get these good EEG recordings. And as you mentioned, they're on a cocktail of different medications, anti-epileptics. In Finland, they do a lot of cooling, which they have evidence that works. So they cool the really sick babies. So no, we could not disentangle this with the data that we had. We've since had NHMRC funding and more collaborations with huge international consortia, and are trying to work through all of this at the moment. But, you know, it's a difficult question because the sicker the baby, the better our metrics work, but the more medications they're on. You can't easily unconfound these effects. But, you know, that's the nice thing about physics, is we have this equation that speaks to an energy principle, and therefore it's got some biological face validity, which I think, you know, makes sense. The really sick babies, their synapses just don't have the capacity to fire discharges. And when they do, it's almost like a mini epileptic seizure, and it gets halfway through one discharge and it's already out of energy. And that's what gives rise to the asymmetric shapes that we see. So I have hope. It's not just a phenomenological description,
Right.
but there's certainly a lot more work to be done on that.
The questions are coming through. So Erin Madden, again, thanks you for a fascinating talk, but wants to understand the concept of a scale-free system. What does this mean for capturing the neurophysics of cortical, subcortical networks?
Yeah, most of what we've looked at here, thanks for the question, is purely cortical, because EEG is most sensitive to cortical activity. And there are extraordinarily complex processes of maturation. There's an end growth plate or something coming up under the cortex. The thalamus is coming into play. There's neurons going up and down. But we do see the emergence of rhythms as well, like the alpha rhythm, which suggests that there are subcortical loops that are happening. Nonetheless, even though there's rhythms and some scales of activity, the amplitudes, you know, they coalesce just like the particles I was talking to, and they sort of run away with this pathological synchrony. Sometimes that runs out, it's a small one, but with some balanced likelihood, it can run all the way away to being a very large burst, 6 orders of magnitude larger than the smaller bursts. So it's really that balance of excitation and inhibition that gives rise to the scale-free dynamics. even though there's a lot of structure emerging in the system.
Amir has asked, would fMRI help, although understands that it might be not possible in a newborn baby environment?
I mean, you're very lucky that Samps is not here, because he's a huge fan of EEG and thinks that we need to use it a lot more and that imaging is very expensive. There are some fMRI data sets on these babies. I haven't looked at them. There's also some emerging diffusion data sets with connectomics, looking at emerging connectivity, which I think is very interesting. The neurovascular coupling in babies is very different, particularly in the sick babies with intraventricular hemorrhage. So I would be reluctant to jump into fMRI. I would be more interested in exploiting more of the structure that we have in the EEG data.
Look, final question from Alistair McEwen. Can you include other clinical data such as nutrition to refine the energy input information?
Yes, and this is one of the goals, thanks Alistair, of the larger trans-European collaboration we have at the moment, as well as the medications that Matthew spoke to, look at other indicators of nutrition. There's also some animal neurophysiology that is being embarked upon when you can obviously experimentally manipulate newborn EEG, and you can also, even in the fly, give anesthetic agents to get some insights into what's happening pharmacologically and neurophysiologically. But so I'd love to say yes, but the work just hasn't been done yet.
Look, Michael, I think we'll end it there. Thank you again for joining us for the symposium and contributing a really fascinating talk, and we look forward to the developments in the future years.